Hi, in this lecture we are going to cover carboxylic acid derivatives, nucleophilic acyl substitution reactions. As you remember, in the previous lecture we covered naming of carboxylic acid derivatives. In this lecture we are going to start from nucleophilic acyl substitution reactions. Okay, let's start nucleophilic acyl substitution reactions. Before starting, let's remember the reactions that aldehydes and ketones can undergo. In the previous chapters we have seen that aldehydes and ketones, they undergo nucleophilic addition reactions. What is the nucleophilic addition reaction? If you have a nucleophile, the nucleophile adds itself to carbonyl carbon, then we form a tetrahedral intermediate. This tetrahedral intermediate can be protonated by an acid, then we form an alcohol. So, why aldehydes and ketones they don't undergo substitution reactions? Because when an aldehyde and a ketone undergo substitution reaction, the leaving group can be either a hydride or can be a carboanion. And we know that hydrides and carboanions are very basic and they are very bad leaving groups. However, a carboxylic acid derivative can undergo a nucleophilic acyl substitution reaction. What happens in these reactions? A nucleophile adds itself to carbonyl carbon. We form a tetrahedral alkoxide ion intermediate. Then we form back the carbonyl bond. Then one of the group can leave. So in carboxylic acid derivatives, this group generally can leave. It's a better leaving group than hydride or ketone. Let's look at a question here. Show the mechanism of the following nucleophilic acyl substitution reaction using curved arrows to indicate the electron flow in each step. First of all, let's identify here what is our nucleophile. We have sodium methoxide, it's an alkoxide, so negatively charged methoxide is going to be our nucleophile. So what's going to happen? Again, nucleophile will add itself to carbonyl carbon. Let's add also lone pairs. Then we are going to form a tetrahedral intermediate. What's this tetrahedral intermediate? Let's show it here. And let's put methoxide part here. And then we know that we can form carbonyl bond again, and this group is a good leaving group. Chloride can leave, and we can form this molecule, which is an ester basically. So this is one of the examples for nucleophilic acyl substitution reaction. What kind of factors affect the rate of nucleophilic acyl substitution reaction? The first one is steric factors. You remember that from nucleophilic substitution reactions, when we have a substrate sterically crowded, the incoming nucleophile will not be able to approach. It's the same case if you have a carbonyl carbon having an alpha carbon with 3 substituent. This reaction will be the slowest with respect to a carbonyl alpha carbon with 2 substituent, 1 substituent or 0 substituent. Basically this one is going to be the most reactive, this one is going to be the least reactive. The second factor is electronic factors. If you look at different carboxylic acid derivatives here, amides, ester, thioester, acid anhydride and acid chloride, you see that acid chlorides are the most reactive and amides are the least reactive. It's not very visible here, but the blue color in the electrostatic potential map around the carbonyl carbon is more for the acid chloride and less for the amide. What factors or why this is so. We can explain with electronic factors. You remember from electrophilic aromatic substitution reactions, substituent can be activators or deactivators based on two parameters. One, it's inductive electron withdrawing or electron donating ability of the substituent. Second, resonance electron donating or electron withdrawing ability of a substituent. Here, if you compare chlorine versus NH2, we remember that halides are deactivators. Why? Because their inductive effect predominates because they withdraw electrons. In this case, in nucleophilic acyl substitution reaction, since their inductive electron withdrawing group is more than electron donating ability, so this carbon will be much more polarized. It's going to be positively polarized more when we have a acid chloride. But when we have an amide, again nitrogen is electronegative element. It's more electronegative than carbon, but nitrogen's ability to donate its lone pair, we say it resonance electron donating effect, is more than inductive electron withdrawing ability. So for that reason, the carbon will not be much more polarized with respect to this carbon. So basically, acid halides are the most reactive, amides are the least reactive. In this slide, we see a table here. It shows the more reactive carboxylic acid derivatives can be converted to other carboxylic acid derivatives, but least reactive ones cannot be converted to easily more reactive derivatives. Okay, so generally we start with a more reactive one, then we can synthesize least reactive derivatives. Let's look at the general reactions. For example, if you have an acid derivative, it can undergo a hydrolysis reaction, and we can substitute Y. It can be chlorine or bromine with OH. It's going to be a carboxylic acid. Or we can react with an alcohol. It's alcoholysis. We will get an ester. Aminolysis, we get an amide. Reduction, we get first an aldehyde, but aldehydes can be further reduced to alcohols. Or we can have a Grignard reaction. Grignard reaction takes place in two steps for carboxylic, so for acid halides. What happens in the first step? We introduce first alkyl group and we generate a ketone. We know that ketones are reactive towards Grignard reaction again. We can introduce the second alkyl group, then we form an alcohol. So let's solve a general question with respect to reactivity and reactions of carboxylic acid derivatives. Let's start with this one. Rank the compounds in each of the following sets in order of their expected reactivity toward nucleophilic acyl substitution reaction. Let's look at here. We have an acid chloride, ester, and amide. So we know that this one is the most reactive one. This is second, and amides are the least reactive. You can go back to table. Let's look at here. We have ester, ester, and ester. This ester has 3 chlorine. This ester has 6 fluorine. So basically, when you have electron withdrawing groups, they will polarize the carbon more, and it's going to be faster, or it's going to be much more reactive. So we can conclude that this molecule having 6 fluorine electronegative atoms, so it's going to be most reactive. One, this is second, and this is third, least reactive. Let's look at the next question. The next question asks us predict the products of the following nucleophilic acyl substitution reaction. Here, what is the nucleophile? A hydroxide. What's going to happen? hydroxide will substitute this methoxide, so we will get here a carboxylic acid. So let's just write here, instead of this one we will have OH. Here instead of this one we will have amino, it's an amide, plus HCl. Don't forget, if you write here NH3 is going to be positively charged. Here the chloride will pick up that hydrogen, and this is going to be a neutral amide. Here this part is the nucleophile methoxide. So this is symmetric anhydride. You can maybe just show it this way, this and this part will leave. So you can say that CH3CO and OCH3. So this part will be CH3. We get an ester. And the last one, we have here an amine. Nitrogens are, nucleophilic. It attacks here, will kick this one. So let's say this one NHCH3. We don't say NH2 because the nitrogen will be positively charged, so we don't get positively charged amides. So this is an amide. Okay, the next, reactions of carboxylic acid. So when we have carboxylic acids, we can convert them to other functional groups or other carboxylic acid derivatives. The first reaction is conversion of carboxylic acid into acid chlorides. You remember from previous chapters when we have alcohols, and alcohols can be converted to halides by with the help of thionyl chloride, SOCl2, thionyl chloride. So let's write the reaction. Plus SOCl2, it's going to be RCl plus SO2 plus HCl. So basically we generate a alkyl halide. The similar reaction happens between a carboxylic acid and thionyl chloride. OH will be replaced by Cl, so carboxylic acids will be converted to acid halides, or acid chlorides in this case. So this is the reaction mechanism. So again, let me just show a little bit mechanism here. If you have RCOOH plus SOClCl, what's the first step? This attacks here, opens up, then close back, chlorine will leave. So we generate this one. The second, the chlorine that left here is going to attack here. It will form a tetrahedral intermediate, collapse back. Now this part is a better leaving group. Then we form an acid chloride. So that's the reaction mechanism. The second type of reaction, conversion of carboxylic acid into acid anhydrides. Basically, this is the industrial way of synthesizing acetic anhydride from acetic acid. When you have like unusually high temperatures, you can have the dimerization reaction and we get anhydride. But we don't generally use in the labs this type of reaction. Second, the third reaction, let's say, conversion of carboxylic acids into esters. There are a variety of ways that we can convert carboxylic acids to esters. The first one is a SN2 reaction. So what happens when you have a carboxylic acid? I will write here the general mechanism. When you have a carboxylic acid, let's say I'm going to give you acetic acid. If you react acetic acid with sodium hydroxide, it's an acid-base reaction, right? We generate an acetate anion, which is kind of a good nucleophile, and this plus water you can write. Okay, and this is the sodium, the counter cation should be here. But this part is going to be our nucleophile. Nucleophiles can attack substrates bearing good leaving groups. For example, here we can synthesize methyl butanoate. So it's an ester. The second way of ester synthesis we call Fischer esterification reaction. Fischer esterification reactions involve a carboxylic acid, an alcohol, and a catalyst. Generally it is acid or base catalyst. So what happens? Basically, it's a equilibrium reaction. It's an equilibrium reaction. How can you shift the equilibrium into products more? As in this case, we use excess amounts of alcohol, or you can use alcohols as solvent. Then they will be very, very excess, and you can get the product. So, how a Fischer esterification reaction happens? Basically, in the acid catalyzed Fischer esterification reactions, first we protonate the carbonyl oxygen with the acid. Think of that, this is HCl, or hydronium, you can even think of that. Then what happens? Alcohol will act as a nucleophile and is going to attack the protonated carbonyl carbon, because when you have protonated carbonyls, the carbons are much more electrophilic, because oxygen, they don't like positive charge, so they want to attract the electrons more to be neutral. That's the reason why the carbons are much more electrophilic. Then we form this tetrahedral intermediate. What happens to this tetrahedral intermediate? This protonated alcohol part loses one of the protons to the neighboring OH group, and then what happens? By the water, we pick up this proton, we form back the carbonyl bond, then water leaves as a leaving group. So this in this way we can synthesize esters. Basically, if you practice writing reaction mechanism, it will help you in future. Let's look at this question. How might you prepare the following esters from the corresponding acids? Basically, we can use two techniques, right? One is the SN2 reaction. The second one is Fischer esterification reaction. We can show both of them actually, but don't forget the limitations of substitution SN2 reactions when you do it. Okay, let's look at here. Let's do an SN2 reaction here. So basically this part is going to be our nucleophile. So use this acetate nucleophile, and here 1, 2, 3, 4 carbon, use iodine as a leaving group and 4 carbon by SN2 reaction. So this will attack here and this will leave, right? So this is one way, it will give you this. The second way, let's use Fischer esterification reaction. What we have to use? We have to use carboxylic acid and alcohol acid catalysis, right? Let's write the carboxylic acid. Let's write the alcohol. Okay, then it's a equilibrium reaction, HCl, and it will give you this product. So basically, I think one exercise should be enough. Conversion of carboxylic acids into amides. I will cover this part in the next lecture. Thank you so much for watching.